Okay, thank you very much for the introduction. And hello, everyone. I hope that you can all hear me and you can see my slides. Um, so it's joint work with Wojciech Janczewski, who is my PhD student at University of Wrocław. And it will be about the very classical longest increasing subsequence problem, but with a twist. And the twist will be that it's a dynamic version of this problem. It will be based on two papers. One is published and the other is not. You can find both of them on arXiv. Okay, so let me first recall the definition of the longest increasing subsequence, even though all of you know it. So we consider an array of numbers, a sequence of numbers A, A1, A2, and so on. They could be integer numbers or real numbers. It will not matter for my talk. And we want to find a subsequence. So a sequence of increasing indices I1, I2, up to IL, such that the elements at those positions are strictly increasing in the array. And we want L to be as large as possible. So this is the usual longest increasing subsequence problem. And if you are teaching basic algorithms first, then probably maybe you give this exercise to the students to come up with an n log n time algorithm for finding the largest L. And there is more than one, but the one that would be relevant for my talk, I will call this Fredman's algorithm, even though if you look at Fredman's paper, he attributes the algorithm to Knuth, and if you look at Knuth's paper, he says it's well-known or something like that, so I'm not sure who was the first one. So it's called, sometimes it's called patience sorting. It's connected to some kind of game on cards. Okay, so this is the algorithm. We maintain an array. Initially, it's some minus infinity in the first entry, well, 0th entry. Then we go over the sequence, and we do some kind of binary searching over this array R. And then we update one entry. So probably you have seen this algorithm. Okay, and the important property is that those numbers are, so I will be the smallest possible element that could end an increasing subsequence of length I in the already considered prefix of the input array. And furthermore, if you look at the elements that get assigned to Ri, you will obtain a partition of the array into L decreasing subsequences. So it's an algorithmic proof of the Dilworth's theorem for the special case. So this algorithm will be useful in a few minutes. So that's why I'm showing it. Okay, so what do we know? Well, so we know that this algorithm takes n log n time, so we have an upper bound of n log n. And there is an old paper by Fredman from 75. He showed that in the comparison model, so the comparison model is that you can only compare two elements as the only operation that you can do. This is optimal, so you need n log n comparisons. It's slightly more difficult than the, let's say, sorting lower bound, but not very difficult. Okay, so in the comparison model, we know what's the situation. If you allow some more powerful model like the word run model, where you can play some tricks on bits, you assume that the input numbers are integer numbers and you can, say, multiply them or do even more fancy stuff, then you can achieve n log n time by plugging in some better predecessor structures. I am not going to torment you with that because this is not the point of this talk. And the last paper in this line is from 2010 by Porat and Kochmore. They show that the length of the longest increasing subsequence, I will refer to as Lis, okay, in the further part of the talk, can be found in n log k time, where k is the length of the result. So if the result is very small, it's slightly faster. Okay, so this is known for a static version of the problem. You are given this array. You need to output the largest L or the corresponding subsequence, and we know what's the situation, what are the best bounds. There is something left to do for the space-efficient algorithms, but I'm not going to go into this direction. So what I would like to consider is the dynamic version of the problem, and by dynamic I mean that you are given an initial array, and then does some updates. And there could be many types of updates. So the natural, simplest natural update would be substitution. So someone is telling you that now you should change the element at the 8th position to some other element, and you should report the length of the longest increasing subsequence, and again and again. So after each update, you should report the length. And maybe if someone asks you and you feel like it, you would output the sequence itself, but the sequence could be long, so I don't want to output it on after every output, after each update. Okay, so substitution is one possibility, but it's more, well, a more general version is that you have insertions and deletions. By insertion, I mean that you have the array, and then someone tells you that you should insert new element 5 at position, well, let's say between 7th and 8th position, okay? So you should move a new element between two consecutive elements on the previous array. So that's an insertion operation. And the other operation is deletion, which is that someone tells you that now you should remove the element at position 11 in the current array. So those are the two outputs. Okay, so I hope it makes sense. What I mean by dynamic list. Okay, and now you can observe when you try to play with this. So in this example, I have shown the longest increasing subsequence. So those elements are underscored, and hopefully it's the longest subsequence is unique. I think it is. And now after inserting 5, you can see that the so you can see that because you insert just one element, L, the length of the longest increasing sequence can change by at most 1, okay? Because you have just one new element. So even though the L that should output change by 1, the witness, which is the corresponding subsequence, might change dramatically. So before 5, it was 2, 4, 10, 14, and 20. And after inserting 5, it turns out that you need to take 2, 4, 6, 7, 8. Okay, so 7 and 8 were not part of the previous longest subsequence. So even though the answer doesn't change by much, the witness might change, and probably you need to somehow to well, maybe not store explicitly, but you need to keep track of this witness. So this is difficult. That was insertion, and here is an example of deletion. So here we remove element 14, and again it's specified by giving the index in the current array, and we renumber the indices after each insert or update operation. And again, the length of the answer will change by at most 1 after a deletion, but the witness might change significantly. Okay, so this is the situation. And I should also say that people have considered many other problems, like classical problems, in the dynamic setting. So it could be a graph, and now you change the graph. Maybe you add edges, maybe you change the weights of the edges, so things like that. And it seems that in many of those problems, the goal is to, first of all, to achieve a sublinear solution. So you want to implement each update faster than by recomputing it from scratch. So it should be sublinear. So that's the first goal. And if you manage to do that, the second goal would be to determine whether you can implement an update in polylogarithmic time. Could be amortized, could be worst case, but the interesting question seems to be, is this polylogarithmic or not? Or just slightly sublinear? So this is the type of question I would like to consider for this problem, for dynamic arrays. Okay, and for insertions and deletions, it's not so clear because this witness might change significantly, but you could start with something simpler. So you could start by just appending or prepending, whatever you prefer, elements of the current array. And from this Friedman's algorithm, you can easily see that if you only append, you can implement each append in logarithmic time because this algorithm was scanning through the input from left to right. So okay, so just appending is easy. If you only prepend, it's also easy because you run the algorithm from the other direction. Okay, but if you do both, if you want to implement both prepending and appending, it's really not clear what to do. I mean, how to modify this simple. Okay, it was a very simple algorithm, but it's not clear how to modify it to support both appending and prepending. So even that seems maybe not so easy, and we want to do even more general queries, well, updates. So what's known for the more general updates? Well, there is this unpublished, I think it hasn't been published. It's a preprint on archive from 2013, so I guess it's not going to be published, by Chen Chu and Pinsker. And they show the following. If the length of the current longest increasing subsequence is L, they can insert or delete an element in time roughly L log n over L. Okay, so if the current list is not too large, this is sublinear, but it could be also large, and then it's you don't get any improvement on the recomputing from scratch. Okay, and after this paper, there was nothing till this year, well, actually last year, because the preprint was available last year. Kociołaka and Sedizhin showed that you can actually maintain full dynamic exact lists in sublinear time, and here sublinear means n to 4 over 5. Okay, so it's an improvement in the exponent. And it's a randomized Monte Carlo algorithm. Okay, so it's better than sublinear, but well, not polylogarithmic. So now the question is, can we hope for a polylog update algorithm for this problem? And I want to show you a partial answer to this problem. We don't have a complete answer, but so it's an answer for a slightly more general version of the problem. More specifically, I will consider longest subsequence problem in which the elements have weights. So you don't want the longest increasing subsequence, you want the increasing subsequence with the corresponding elements having the largest sum of weights. And I will define this formally in a minute. And for this problem, we're able to show a conditional lower bound, and it turns out to be not very difficult. And it follows from there was a paper by Abud and Dalpat in Fox 2013. They showed some kind of general framework for showing that many problems, dynamic problems on planar graphs, do not admit very efficient dynamic algorithms. Very efficient means, in this case, faster than n to 1 over 2 minus epsilon. So you can do square root of n. For many problems on dynamic problems on planar graphs, you can do square root of n, but they show that probably you cannot expect anything faster. And I will define what probably means, because this is not a probabilistic statement. It's they use some kind of conjecture. Well, they use the APSP conjecture, all pairs shortest paths, and probably you have seen this in some versions. So this conjecture says that if you have a weighted graph and you want to compute the shortest paths, well, the distance between each pair of vertices, and you have n nodes, then this takes roughly cubic time. You can hope for some polylog improvements, but there is no n to 3 minus epsilon time algorithm for this problem. And you have defined the problem exactly, I mean, how large are the weights and so on, but I'm not going to do this that precisely. Okay, so assuming this conjecture, they show that for many problems with dynamic planar graphs, you cannot expect a fast algorithm. And the idea in the proof was that this actually considered a very special planar graph. It was basically a grid graph, or more specifically, 2 grid graphs. So the left part, the right part, and the middle part. And it's a weighted graph. You have some weights on the edges. And the idea is that using distance queries in this graph, so there will be distance queries between pairs of nodes, and we'll change the weights on some edges. And using them, they can simulate the mean plus product of 2 matrices. Mean plus product of 2 matches A and B means that for each I and J, you should find K such that AIK plus BKJ is smallest. It's known that if you can implement such products efficiently, you can compute distances between all pairs of nodes by doing log n invocations. So it's enough to consider mean plus product. So the idea was to encode matrix B in the left part of the graph. So it's like a n times n grid, essentially. And you look at Bij, it's some value, and you put this value on the weight of some edge in the left part. So this is how you encode B. For A, you take each row of A, so you consider the rows 1 by 1, and you put you encode the rows in this middle part. So again, you modify the weight of the edge. Okay, in the right part, you don't really do anything depending on the matrices. The edges have some fixed lengths. It's not so easy to. I mean, you have to think a bit how to adjust those lengths. I'm not going to show you that. But if they did it in such a way that by querying about the distance from A1 to A prime 3, they will find Cij. So they will find K. K is an index in this middle part, such that AIK plus BKJ is smallest. Okay, so then Then it means that the number of updates that you do to your matrix is n squared, because you have to encode B, and then you process rows of A one by one, and you encode each of them. And then each entry of C of the output matrix is one query. So you do n squared queries and updates. The APSP conjecture stipulates that together it takes cubic time. So it means that query or update takes at least linear time in n, and n is the square root of the size of the graph. So this is how they achieve this lower bound. Okay, but this is for planar graphs, and I promised you longest increasing subsequence. So how does it relate to longest increasing subsequence? So first, it will be convenient to think about a set of points instead of an array. And the natural way to do this is that you have an array A, and you convert AI into a point AI. Okay, so you obtain a set of points. And now the longest increasing subsequence becomes a chain. I will call this a chain in the plane. So it's a sequence of points with increasing x and y coordinates. So from now on, I will talk about a set of points. It's a dynamic set, so you insert, remove points. And after each update, you should report the length of the longest chain. And it's not hard to encode this back as an array. So you just write down the points from left to right. So it's equivalent up to log factors, because you need to somehow keep track of indices, but this can be done in log time. So it's not too time consuming. And now we can modify their construction. So essentially, we again have two grid graphs. Okay, and there is a bunch of points. I'm not going to show you the details of that. So there is a point in each cell, sometimes 2 points. The weight of a point encodes the entry of the matrix. So in the left part, there is the matrix A. In the middle part, there is one column of matrix B. So you adjust the weight of a point. You add the entry of the matrix to this weight. And then when you do this carefully, then it turns out that the distance in this planar graph is just the length of the longest chain from one point here to some other point here. So if you can implement slightly more general queries, so those are not queries about the longest subsequence in the longest chain in the whole input. I want to specify 2 points, and I want to ask about the longest chain connecting those points. This corresponds, if done carefully, this corresponds to the shortest path in the planar graph from the previous slide. So the only difficulty is to now to somehow overcome the fact that we don't have such queries. We can only query about the length of the longest subsequence in the whole input. So to do that, you just add infinity to the weights of those 2 points. So then it's you really want to take them in your longest global chain. And by how those grid graphs are created, and I would have to go through the details, and I don't want to do this, then the longest chain will be exactly like that. So you need to make the weights of the points to increase significantly when you go from right to left in the left part, and in the other direction in the right part. So you need to control that somehow. Okay, so it means that if you believe the APSP conjecture, that then you cannot solve the full dynamic list for a set of weighted points in smaller than square root of n time. Okay, again, square root of n because you have n squared points encoding n times n matrix. Okay, but those are weighted points, which is not the standard assumption. So what about unweighted instances? So it's tempting to think that you could take those points, they all have their weights, and you could replace a point of weight 9 with 9 points, okay? And then this part works okay. The problem is with those 2 points with weight infinity. Of course, you don't really need infinity, you want sufficiently large number, and it's polynomial in the end actually when you do the simple calculation, but it turns out to be too large. I mean, it just breaks the lower bound. It still gives us something if we assume more general queries. We call them extended list queries. They provide the length of the longest increasing subsequence in a range, not in the whole input, but in a range. And then it's enough to translate this reasoning. The only difference is that now we cannot use the APSP conjecture, because in the APSP conjecture, we have 2 matrices, and the entries in the matrices are actually quite large. They are large integers, and you would need to simulate each such entry with many points, so the size of your input explodes. Fortunately, there is some other conjecture, probably fewer people believe in the other conjecture, but still it's called the online Boolean matrix vector multiplication conjecture. So in this problem, you are given one Boolean matrix, M. You can preprocess it in polynomial time. And then you are given Boolean vectors V1, V2, V3. And after having seen VI, you should output the Boolean product of M and VI. And then after you have done so it's a vector again, okay? Then you get VI plus 1 and you should output the next vector. And it's important that you have to output the result before seeing the next vector. Essentially, this is what's stopping you from using Subsequence, one of the faster algorithms for this problem. And we don't have a subcubic algorithm for this problem. So you have n vectors and the total time is cubic. This is all we know, but we don't know whether it's true or not. That, there is no such algorithm. So if we use this conjecture, then we get that for the extended queries, dynamic list can be solved in n1 over 3 minus epsilon. So the exponent is slightly smaller because we have to simulate weights with many points. So the size of the input increases. Okay, that was some lower bound, but not for the exact problem that I want to consider. So why did I bother you with that? Well, I wanted to give some justification for why we work with approximate version of this problem. So the exact version, I mean, we don't know what's the best possible answer. The best upper bound is n2 of 4 over 5 from last year. We don't know whether polylog is possible. But it seems that we don't know. For the modular queries, it's not possible. So it's natural to consider approximation of the longest increasing subsequence. And the natural way to define approximate version of this problem is to talk about alpha approximation. And alpha approximation is that you should output a number from L over alpha and L, where L is the longest increasing subsequence. Okay, so this is the alpha approximate longest increasing subsequence. And there was a paper by Mitsamathan and Sedijin in Stock 2020. So they showed that you can maintain, some approximation, yeah, 1 over epsilon to 1 over epsilon with some constant factors. Under insertions and deletions in n to epsilon time with some polylogs. So in other words, you can have constant approximation in arbitrarily small polynomial time. So for an epsilon, you have constant approximation with constant depending on epsilon, and the insert update time is n to epsilon. Okay, and let me show you, and we show a better bound. So let me first show you how did they manage this and what's the difference in our approach. So in the remaining part, I will always think about the set of points, I and AI. And furthermore, I will consider the decremental version. So I will delete, in the very end, I will show you one slide about making it full dynamic. It turns out to be not so difficult. The decremental version is already difficult enough. Okay, so we want to maintain approximation of the longest chain in the current set of points. And then there are deletions. So someone is telling you, delete this point, yeah, and you do that. And keep in mind that we don't really change the x coordinates after deletions. We only delete and we keep the same x coordinates. And for deletions, it's okay. If it's full dynamic, it's not okay. So you have to add some extra layer of translation between the current coordinates and what's given in the inputs. So I don't want to do that. Okay, so we want to do this. And they have this nice framework. It works as follows. So they partition the current points by choosing a grid. So it's B times B grid. They choose evenly spaced X and Y coordinates to define the grids. And they say that they will create, it's a recursive algorithm, well, data structure. So they maintain the longest chain, not only in the whole set, but also in every box, in every cell, and also in some other subproblems. So the other subproblems are always it's a rectangle. So it's a rectangle consisting of a complete number of blocks. How it's defined exactly, I don't want to show you, okay, because it's a bit technical. But in particular, for each row in this big matrix, you will have a subproblem corresponding to the whole row and the whole column. And then they show, so you have instances corresponding to this column and this well, not the whole row, but part of it. And then they say that it's enough to consider very special increasing chains that look like that. So you take, you go to the right in the row, okay, and then you go up, and then so you disregard. Maybe in the longest chain you would take some points here and some points here, but here you disregard them. So you lose a little bit. And they show that this only incurs a factor of 2. So but if you check all possibilities, one of them is better, and it incurs a loss of factor of 2. But now you have a subproblem. You can compose the longest chain by querying those smaller subproblems. So you will have a subproblem corresponding to this part, and you will query it, and you will have a subproblem corresponding to this part, and you will query it. So you can compose things together. It's a very high level overview, and then it's done recursively on a constant number of levels, but the constant depends on the epsilon. So you lose factor of 2 in each level, and there's some clever calculation to bound this whole thing. Okay, and when you do an update, then instead of recalculating n values, you only have this grid. It's b times b grid, and roughly speaking, time to recalculate it. And b is smaller than n, so that's how they achieve a sublinear running time. Again, this is a very high level. Please look at the paper. Okay, so we use a different approach. The first step, well, we also have a recursive structure. So we have the whole set of points and then some other sets of points. So now I want to show you what are the set of points that we consider. Let me first define a dyadic interval. So a dyadic interval is just you have some power of 2, and you have I times this power of 2 and I plus 1 times some power of 2. So you can think about complete binary tree built on the coordinates, and each node corresponds to such an interval. So we consider all rectangles with the x and y coordinates being dyadic. Okay, so this is what we do. And you can observe that even though there are many intervals, there are many rectangles that are defined like that. So the n squared of them, okay, you have n ranges on the x coordinates and n ranges on the y coordinates. You only have n log squared non-empty rectangles. Because when you think about single point in the set S, it belongs to log n ranges on the x coordinates and log n ranges on the y coordinates. So overall, each point is inserted into log squared subproblems. So in particular, the number of subproblems is only n log squared, and the total size is small. So for each of such non-empty rectangles, we will maintain some structure. It will not be a recursive structure, so it will be some structure for each rectangle. Okay. So what do we want to maintain for each such rectangle? Well, so we would like to maintain a structure for approximating the longest chain in the rectangle, but for extended queries. So we are in the rectangle, we want to specify 2x coordinates, and we want to get an approximation of the longest chain consisting of points in this rectangle with x coordinates in this range. Okay, so for each rectangle, we want some mechanisms for such queries. So those are, formally speaking, defined that we want to maintain an array. Again, an array and a set of points, it's all the same. And we have deletions of elements and queries about the length of the longest increasing subsequence in a range of this array. And for each rectangle, we want to have such a mechanism. Okay. So the first question is how to implement such queries. And I'm not sure how many of you have seen this, but even in the static setting, when there are no deletions and you want to support computing longest increasing subsequence for each range, okay, so the query is just I and j, and you should output the longest increasing subsequence of integers in the range from the ith to the jth entry. This is not so easy to implement efficiently, but it turns out that there's a structure of size n log n. It can be constructed in n log squared n, and the query time is log n. If you have heard about the Monge matrices or the Monge property, so you can use this to design such a structure. But this structure is really static. I mean, it's not clear how to update it. Okay, so we will use a different approach that I will call list classification. The update time will be well sublinear, but the answers will be approximate, while the small business gives you exact answers. Okay, so what's the idea? So our goal will be 1 plus epsilon approximation of the longest chain, longest subsequence. So to this end, it's enough to to construct multiple levels of the structure, and the kth level of the structure is, roughly speaking, responsible for checking if the answer is 1 plus epsilon to k. Okay, so for different values of k, you have a structure responsible for checking if the answer is at least 1 plus epsilon to k, and then you would just check all values of k, or maybe you do binary search if you want to be slightly faster, but I don't care about the number of logs. So the structure will tell you that there is an increasing subsequence of length 1 plus epsilon. If there is an increasing subsequence of length 1 plus epsilon to k plus 1, the structure should say yes, and otherwise it can say yes or no. So there is this gap where you don't really know. But if the answer is sufficiently large, you should output that. You should output that there is a chain of length of at least 1 plus epsilon to k. Okay, so that's the idea. So how you could implement the structure? So the first attempt could be that, so you have your array, and you think about all intervals I prime and j prime, such that it's a minimal range in which the length of the longest increasing subsequence is 1 plus epsilon to k. So you think about all pairs I prime and j prime, and you take the minimal intervals in which the answer is sufficiently large, and then you store those intervals. Then it's easy to answer a query, because in the query you just need to find if the input to a query is I and j, and you need to find if I and j are fully contained in one of those intervals that you store, and this can be done in like log n time with some range searching structures. Okay, so this is what you could do, but it seems to be hard to maintain because you will store many intervals, and now someone is deleting an element. It might belong to multiple intervals, and then you would need to maybe remove them and create new intervals. So there is a lot for computation. This element could contribute to the witness in each of those intervals, to the longest subsequence. So you would need to do something with them. So this is not really that great. So we introduce a notion of covers. So it's k1, k2 cover for a set of points or an array. It's all the same. So it's a set of segments. A segment is just a range of x coordinates. And in each subsegment, there should be a chain of score at least k1 at most k2. And the guarantee should be that if you specify a range ij, and there is a chain of length k2 in this range, then the set of intervals of segments should contain at least one segment fully inside your query range. Okay, so if you want to answer a query and the answer to the query is at least k2, then in your set of stored segments should be something inside your query, and then you only store segments with answer at least k1. So you would be able to say that the answer to your query is at least k1 if the true answer is at least k2. So again, there is some gap between what you output and what's really the true answer. So in such case, we say that ij is covered by this segment x. So the x can be used as a witness for your answer. And then the important parameter of such covers is the depth. The depth is just the largest number of pairways intersecting segments. So each segment is a range. So it's the click in this interval graph. And this parameter is relevant intuitively because when you delete an element, you only need to update segments that contain this element. So if you bound the number of pairways intersecting segments, you'll be able to bound how many segments you need to possibly compute. Okay, and then we have this property that, so it's not so clear if such covers exist. We need covers with small depth. So with not too many segments containing any position for given parameters k1 and k2. K1 and K2 will be connected to 1 plus epsilon, to the powers of 1 plus epsilon. So it's maybe not so trivial to see that such covers exist, but they do exist, and the depth is K1 over delta. Delta is the distance, the difference between those parameters. And they can be found by a greedy algorithm. So it's when you think about this for some time, it's the most natural. Greedy algorithm, the only difficulty is improving that it works. So let's think about 3, 4 covers. So again, the guarantee should be that if the answer is at least 4, you should output at least 3. That's the guarantee. If you have an interval for which the answer is at least 4, you should have a segment in your set with the answer equal to at least 3. So let's say exactly 3. So what you could do, you could take the, this is the array. You could take the shortest prefix of the array with the answer equal to 4. This is P1. You have 4, 6, 8, and 15. And then you store its shortest suffix with the answer being 3. You add it to the set of segments. So S1 can be used as a witness for P1 because it's inside P1. Then you continue from the beginning of S1 and you find the shortest prefix of what remains, where the answer is at least 4. So this is P2. And then you take the shortest suffix of P2, for which the answer is exactly 3. And you add S2 to the set. And then you continue. So in the next step, you extend from this place. Okay, you find the shortest prefix for which the answer is 4, and you take the shortest suffix for which the answer is 3, and you store this as the answer. Okay, this continues. Hopefully, there's no mistake in this example. Okay, so this is a greedy algorithm. You need to to see what's the depth. So for instance, the depth of 14 would be 3. Because you have 3 segments in your set containing 14, and those are the only segments that you might possibly want to recompute when deleting 14. So that's why we care about depth. Okay, so this is greedy algorithm. We are still very far from the solution because this greedy algorithm was running from left to right. So now someone is removing an element somewhere in the middle, and what do? We're computing this cover from left to right, but it takes linear time. So we are not done. I will show you what needs to be done in a minute. And the other problem, which I maybe want to ignore, is that we need to be a bit careful about what are the parameters K1 and K2 in the definition of the cover. So I've said that there will be just powers of 1 plus epsilon. So each level of the structure would be a cover with different power of 1 plus epsilon. It's slightly more annoying than that.
I have a question, just a tiny detail. So when you compute this this cover in a greedy way, can't you start the next greedy one not exactly from the element of just one next? You can, okay.
You can, but the proof gets more annoying. Yeah, in the paper we actually have 2 versions, and one of them we are doing what you. Yeah, you're absolutely right. You could do that. Okay, so what covers are you maintaining is slightly more annoying because of rounding issues. So you need to maintain whether to round up or down. Like 1 plus epsilon to k could be a very small number between 1 and rounding issues when you try to do the calculations. So the first few levels are just exact covers, like 1 cover, 2 cover, 3 cover. So if the answer is like pollock, you will know the answer exactly. The approximation kicks in only later. Okay, so this is a technical issue. The more annoying part is that to recompute the cover, I mean, you would need to run this greedy algorithm from left to right. It takes linear time, the number of points. We cannot do that. So somehow we need to avoid recomputation after each deletion. Okay, so here is what we can do, and it uses the fact that we define the family of rectangles in this funny way with dyadic intervals. So the observation is that, let's say that you work with this rectangle. So you want to maintain a cover on one of the levels. So whatever I'm going to present now, it's being done on each level of this family of covers. So now fix one level. And now we want to maintain a cover for this rectangle. So recall that a cover, the purpose of a cover is to capture each possible query. So when you have a query from I to J, and the answer in this range is sufficiently large, in your cover you should have something that covers that. Okay. So now when you think about this rectangle, you can partition that into left and right part at a power of 2. And the left and right part would be still in your collection as long as they are non-empty. So you can partition in the median x coordinate. Well, not the median x coordinate, just the median x value. Okay, so if you are from x0 to x1, you take x0 plus x1 and you divide by 2. And you have two smaller rectangles. So then when you think about the query range, if the query range is fully on the left of this middle x value, you can take the cover from a smaller rectangle, because the smaller rectangle was in your collection, and any query there is actually covered by what you maintain recursively, probably. And the same on the right. So the only queries that you should worry about are the ones crossing the middle x coordinate. Okay, so like I'm sure this is very visible, but this is a query that crosses the middle x coordinate, and only those need to be taken care of for the larger rectangle. So the cover for each rectangle will be the union of the cover from the left part, the right part, plus some extra segments that are supposed to take care of the queries crossing the middle x coordinate. Okay, so it's slightly better. We don't have to recompute from scratch. We can reuse something. It's still not enough because each recomputation is still expensive, and you might have many points around the middle x coordinates, so it's not what to do. But you don't have to recompute after each deletion. Well, you want approximation, so you can wait a little bit, okay? If in the approximation algorithm, you want to distinguish between the answer being, I don't know, L over 5 and L, then you can, after you recompute, and you choose the parameters in the cover to be a bit more tight, then this cover can be used for a few more deletions, because each deletion changes the answer by 1, okay? So if you change the parameters, you can wait a little bit with the recomputation. So formally speaking, if the cover returns implicit sequence of length L, then if you update only after epsilon times L updates, then the approximation factor becomes 1 plus epsilon. It gets multiplied by 1 plus epsilon. So that's probably okay. To show that it's okay, you need to look at the parameters and adjust the parameters. There are different levels of this process to make it all work. There's still one missing part that I want to briefly describe, namely recomputing this middle part of the cover. So the segments that are supposed to take care of the queries crossing the middle x coordinate. So the time for that should be roughly proportional up to log factors to L. So even if you have many points in this middle part, it needs to be bounded by L, because you do this once you have done roughly L deletions, epsilon times L deletions. So that's your time budget. Okay, and the third trick, and well, the last trick, is that this can be done by querying the covers from the up and down part. So let me just show you what I mean on the figure. So this is the rectangle for which you want to compute something. And now we have different cases. So, okay, so x1, x2 is is the whole rectangle, xm is the middle x coordinate, and we also consider the middle y coordinate. And now when you think about a possible chain, it's partitioned into two parts with smaller y coordinates than ym and larger coordinates than ym. And now the thing is that this first part is relevant from the bottom rectangle. So if the bottom rectangle is non-empty, you have maintained a cover for it. So you have something that approximates this first part of the chain in the smaller problem. And the same for the upper part of the chain. In the upper rectangle, you have stuff that approximates this upper part of the chain. So maybe it's a bit shorter, but it approximates it. So now the idea is to extract some of the segments, some of the chains from the upper and lower part, and concatenate them. You have to think about a few cases. They depend on how the chain that you seek intersects with xm and ym. So those are the cases. The bottom line is that, let's think about this one. Okay, let's think about this case. The bottom line is that in this case, from the bottom rectangle, you're extracting a segment that intersects xm coordinate. But the definition of a depth was a bound of how many segments can intersect one x coordinate. So if in the bottom part you have small depth, then you have not so many segments that can be possibly used in this bottom part. So you have to use this notion of depth. This gives you a bound on how many segments you need to extract from bottom and top. You just extract all of them. It's polylog of them, and each of them will be of length roughly L. L is the length of the increasing subsequence, the chain that you are currently considering. So you have L times polylog elements in total that are interesting for you. You extract all of them, so you extract polylog chains. Each of them is of length L. You take all those elements, you arrange them in an array, and you run this sparsification, this greedy procedure that goes from right to left to right. But now it works on the array of length L polylog. So this is okay. Okay, it was high level. Hopefully it gives some intuition. Then you need to adjust the parameters. On each level of this process, you make the approximation factor worse because you apply sparsification, and also you wait a little bit for sufficiently many deletions to happen. So you keep losing approximation factors on different levels, but it goes bottom up, so it can be controlled. You need to make the guarantee on the approximation depend on where you are in this decomposition. What's the height of your rectangle? And you have to play with the logs. So I promised polylog. Here is a polylog with log to 10. Okay, and the important part is maybe the dependence on epsilon. It's polynomial, not exponential. So the previous solution, and well, the same for the running time. It's log to 10, but it's log not 10 to epsilon. Okay, and now I hope I still have some time. I want to show you one application that I find cute. Okay, if you can use such a word, I'm talking about the problem. So there's a lemma, Erdős-Sekler as lemma. It's about a partitioning of a permutation. Maybe there's more than one. Okay, but there's one about a permutation. When you have a permutation on n elements, it can be decomposed into well, big O of square root of n increasing and decreasing subsequences. Okay. There's also one about convex polygons, but I mean the one about permutations. And one way to show this is to use this well-known fact that when you have a permutation of R times S plus 1 elements, it contains an increasing permutation of subsequence of length R or decreasing of length S. Okay, so you keep applying that and you just extract the longer one repeatedly. So now the question is how fast you could implement that, and maybe even before that, why would you want to implement this faster? So the idea is that you might hope to use this to speed up algorithms. So you have a general permutation, you're not sure what to do with that. So you decompose it into monotone permutations that are much easier to deal with. And then you compose whatever you want to do for those monotone permutations. I don't have an example for permutations, but for other problems, modular problems, it has been used. So we decompose into a nicer subproblems, and then we compose the solution from those. So there was a paper, well, if you do this naively, the running time is n to 1.5 times log n, because the root n iterations, in each of them you run this Friedman's algorithm n log n time. And there was a paper in 98 by Gawrychowski and Fogel. They shaped log factor. It's actually not so easy to do that. You have to control, you have to reuse the computation, you have to maintain a decomposition of anti-chains, and you have to update it. So it takes some work. But now we can use our result. We can set epsilon to be 1. So it's just a constant approximation in polylog time. And we can just find this decomposition into O tilde n time. So we just find the longest increasing subsequence. If it's longer than the root n, if the approximation is larger than root n, we just extract it in polylog time per element. And when we are done, we know that the increasing subsequence is at most root n times polylog. So we can run Friedman's algorithm to decompose into root n times polylog decreasing subsequences. Okay, and the running time will be n polylog. You can play with the constant a little bit. The best constant, it's a nice puzzle, never heard, but nice, is that square root of 2n is the optimal constant in this decomposition. Okay, so we cannot get that, but we can achieve 1 plus epsilon times square root of 2n in O tilde n time, but the constant depends on epsilon. You could have also used this previous algorithm by Mixmath and Stringent. They have a note on archive that describes how to do this, but the running time would be n to 1 plus epsilon. So it will be not almost linear. Okay, it will be close to linear, but not almost linear. Okay, that was all for decremental, and the application was also for decremental. And actually, the application was why we look into this problem in the first place. But then we want to have a fully dynamic algorithm. In some cases, there is a gap between decremental, incremental, and full dynamic. In this case, it turns out to be not super hard. The main problem is that we cannot have a fixed collection of rectangles. Those dyadic things don't really work, because now you might have insertions in one place, and it's you lose control on the height and everything. So we use a different recursion. If you know 2D range trees, and probably you do, it's a recursion very similar to 2D range trees. So it's divide and conquer on the one coordinate, and inside each problem we do divide and conquer on the other coordinate. So the rectangles are less nice. Now we don't have this guarantee that we can decompose into left, right, top, bottom, but there is still enough structure to make this work. There is one more log factor, because there's slightly less structure. And the last part is the amortization. What I've described was amortized, mainly because we have to wait for sufficiently many deletions to happen, and only then we recompute. And this recomputation takes O tilde L time for every roughly L deletions. But this can be deamortized by standard method. So you just maintain 2 copies of each part of the structure. You keep rebuilding in the background, and you use the other one, and then you swap. Okay, so here's the paper with the upper band, and if you check Archive, there is also a short paper with the conditional lower band. And if you want some open questions, so we have log to 10 for the decremental and log to 11 for the incremental, which is quite high. I'm not so sure about getting it down to 2 or 3 logs. Maybe you can shave 1, but or 2. I don't know how, but probably if you spend enough time. But I'm not sure about a reasonable number of logs. We would like to have approximation algorithm for weighted, because we have a conditional lower band for weighted. So it would make sense. This specification doesn't really work, because this it was not sensitive to the weights, and we don't see how to make it sensitive to weights. To different elements have different weights. And the most annoying question would be a condition to get a conditional lower bound for full dynamic exact leaks. Just to remind you, the paper by Kochimaka and Stygin solved this in N2 4 over 5, but we don't really have a conditional lower bound. The best that we could do was for more general queries, where you specify a range of X coordinates, but maybe you don't want this. And by the way, this approximation algorithm that we showed you can actually do such queries. So for this variant, it makes sense. It's a good justification. Maybe that's you should consider approximation, but for exact, it's not so clear. Okay, so those are some questions. And, okay, thank you for your attention.